are going to continue our discussion on different types of formal methods for design verification. So, in the last lectures we saw how we can construct BDDs and represent Boolean functions using binary decision diagrams. And BDDs provide a canonical formalism for Boolean functions. So, given two Boolean functions, we can compare them by creating their BDDs and checking whether they are isomorphic. And we know that the way in which the BDD manager works, if you have two functions using the same BDD manager, then they effectively will point to the same root node of the BDD. So, that way we will know that they are equivalent. Now, that is fine for checking combinational equivalence between two functions. So, maybe a function and its implementation, but it is not good enough to check sequential equivalence or the equivalence between two sequential circuits. So, the mathematics behind comparing sequential circuits has also been well studied, and we are going to look at that. And also another thing that we will look at is how do we use Boolean SAT solvers to perform equivalence checking, not only combinational equivalence checking, but also sequential equivalence checking. So, today's lecture will focus on state machines. We will start with a few definitions and few notions developed around state machines, and then we are going to look at equivalence checking problems with state machines. So, this is the agenda of what we are going to do over the next 2 or 3 lectures. We are going to look at finite automata, equivalence of finite automata from the definition point of view. Then how do we take product of finite automata? Then we look at acceptors for finite sequences and acceptors for infinite sequences, and then we will look at how we use SAT solvers to do CNF satisfiability, and then we are going to look at equivalence checking problem, where we will look at combinational equivalence checking and sequential equivalence checking. And finally, we are also going to look at some algorithms for equivalence checking and state minimization. So, to start with, a finite automaton, a deterministic finite automaton M, which is alternatively called a transducer or a Mealy machine, as you may be aware, is a 6 tuple M equal to Q sigma delta delta lambda Q0, where Q is the finite set of states, sigma is the input alphabet, delta is the output alphabet, and the small delta is the transition function which takes a state and an input and maps into the next state. And then we have the output function, which given a state and given the input tells us what is the output of the state machine, and Q0 is the start state or the initial state. Now, if this is so this is for a finite deterministic automaton, and for most part of our discussion we are going to stick to deterministic automata, but just for completeness, if it is a non-deterministic automaton, then the thing that will change is this one, right? The transition function will change, and just let me take a pen. Yeah. So, how is this transition function going to look like when this becomes a non-deterministic automaton? Yeah, it will be, it is going to map from Q cross sigma to 2 to the power of Q, right? Or in other words, we are going to have this as a transition relation, right? So, we will have delta, which is a subset of Q cross sigma cross Q, right? Is that clear? So, the difference between deterministic and not deterministic automaton is essentially in the transition relation. In a non-deterministic one, it is a transition relation, and in a deterministic one, it is a transition function, right? And here we have seen that in this Mealy machine, by definition, the output is a function of the state and the input. Now, if it is the case that the output is a function of only the state, like here, then we call it a Moore machine. Right. So, this is I believe many of you have gone through this in your second year in switching and finite automata theory. So, this is just a recap of that. Now, we define the path function as follows. Path function is that given a state and given an input sequence, okay. So, n maps to sigma is an input sequence. So, given a state and given an input sequence, it tells us the state that you reach at the end of that sequence. So, what does that mean? That when we are in a particular state of the state machine, okay, let us say this is q0, and I give some input, this takes me to q1, then I give some input I1, it takes me to q2, and like this, and then I reach some q dash. Okay. So, if my input sequence A is I0, I1, etc., to some Ik, right, then we define this delta star from this q0 with this A is q dash. Right. So, this is the, when I present the state machine with this input sequence and it starts from q0, then it ends in the state q dash. Okay, that is what we define by this path function delta star. Okay, we are going to use this from time to time, so it is best to remember that this is the terminology. And remember that this path function is defined because this is a deterministic automaton, right. That is why for an input sequence there is an unique q dash where it reaches, right. For a non-deterministic state machine, this could have become potentially a set of states, right. So, this is a delta star function. Given an input sequence A, we have delta star QA is equal to Q dash, with Q0 is the Q, okay, and Qi plus 1 is delta of Qi AI, where AI is the ith input, and Q dash is the last. So, Q and as many that you have in this sequence, right. We also define a path output sequence. So, this takes a input sequence and the present state and tells us what is the last state at the end of that input sequence, and the path output sequence produces the sequence of outputs corresponding to an input sequence, right. So, given an input sequence A, we have lambda star which is the path output function, is some vector u, some sequence u, where like before q0 is q, qi plus 1 is delta qi ai, and ui is the output produced in the ith cycle, okay, when presented with this input sequence. So, ui is lambda of qi ai. What was lambda? Lambda was the output function. Okay. Is this clear? Now, we define automata equivalence as follows. Two automata m and m dash are called equivalent if for an arbitrary input sequence applied at both automata, the same output sequence results. So, no matter what input you give to the two automata m and m dash, they are going to produce the same output sequence. I do not care what states they go through. I am my definition of automata equivalence as defined here is that if we start the two automata from the same state, then for the same input sequence applied on both of the automata, they are going to produce the same output sequence for every possible input sequence. Clear? So that's what is written here. For all input sequence A, lambda star q0a is equal to lambda dash star q0a. That is the initial state. That is the initial state. Q0 is the initial state. That's where you start. Right? That is where you start. So basically, if you start both the automata and present them with the same input sequence, they are going to produce the same output sequence. Then the two are said to be equivalent. Okay, this is our definition of automata equivalence.
So in the stack, what will be written?
Yeah.
That a bar dot. What does that mean?
Which one?
A bar dot lambda star.
Oh, this is for all A. Then
Okay.
this. Okay, for all A, lambda star q0a is equal to lambda dash star q0a. What is lambda star? Just now we defined, it's the output function. So the output sequence produced by the machine when presented with the input sequence A. Right? Is this clear? Now let us come to the definition of state equivalence. Given two Mealy machines with the same input and output alphabet, so remember that obviously equivalence of two machines makes sense when they have the same input and output, right. So we are given two Mealy machines with the same input and output alphabet. The first Mealy machine is M, Q, sigma, delta, this thing, and this is the second Mealy machine. So they could differ in the set of states, they could differ in the transition function, they could differ in the output function, okay. They could also differ in the initial state, but the input alphabet and the output alphabet are the same, okay. Now the state equivalence relation, which is called this, which is represented by this tilde and which is a subset of q cross q dash, right, because it is taking pairs of states, one from here and saying that they are equivalent. So the state equivalence relation is the largest relation which satisfies the following, that we have q and q dash are equivalent if and only if for all A such that A belongs to the input alphabet, for all inputs A, lambda of qa is equal to lambda of q dash A. So what it means is that for every input, the output produced by M in this state and the output produced by M dash in this state are the same, right. So when M is in state Q, when M dash in state Q dash, if they are presented with input A, they produce the same output, and this applies for every input A, right. So this is condition number 1. Condition number 2 is that the next state that you get when you present Q with A and the next state that you get when you present Q dash with A in M dash, they should also be equivalent. Is that clear? So what did we say? We said that okay, this is my M, this is my M dash, I have the state Q here, I have the state Q dash here, right. I am claiming that these two are equivalent. If they are equivalent, then two things must hold, that for every input A that I produce, for every input A, if this produces an input B, okay, and for the input A, if this produces an input Z, then it must be the case that B is Z, right. So, they should produce the same output on the same input, and if this state is eta and this state is var phi, then eta and var phi must also be equivalent, right. So, what do these two together mean? If these two are equivalent, then again from here the same thing will hold. So, inductively you can say that the output function, the output path function for the two will be the same, in the sense that if I present some input sequence here, some input sequence of inputs, then lambda star this thing should be equal to, if I take q dash and present the same input sequence, then these two should be equal. So, they should produce the same output. Now, this is inductively proven from the fact that we said that they should produce the same output on a single input, and then these two should be equivalent. So, inductively this one is going to hold. Is that clear? So, let us go back here. So, it holds that for all input sequence A, for all input sequence A, q and q dash are equivalent, implies that delta star q A is equivalent to delta dash star q A. Okay. All right. So, this also says that the state that you reach at the end of this sequence is equivalent to the state that you reach here, and the outputs that is produced along the way, which is given by lambda star, will also be the same. Two Mealy machines M and M dash are equivalent, written as M equivalent to M dash, if their initial states are equivalent, right, then everything else is equivalent. Now, see, this state equivalence is a very interesting feature. This not only helps us in comparing two separate Mealy machines M and M dash, but can also be used to compare two states of the same machine M, right, and therefore, the state equivalence definition is also used to minimize set of states. So, if you can find that two states in M are equivalent by this definition, then you can merge those two states. You do not need to have them as two separate states, okay, and that is the basic theory behind state minimization of finite state machines.
Sir, can't we say that all the states that the machine is undergoing when we apply the sequence A, then all the states must be equivalent in the for the two Mealy models?
Well,
like the first statement, I mean that.
No, first of all, you see that they may not have the same number of states, right, but they can still be equivalent, because our definition of equivalence is that for the same input sequence they produce same output no, not same states, same output. What this says is that this
the statement above, it says that the output lambda q comma
this one,
yeah,
this is a single input, given a single input, okay, the output that is produced is the same, all right, but for lambda star also it will be same. Lambda star q an input vector A will give lambda dash star q dash input vector A, right. But remember that the states are, all that we are saying is that the next states are equivalent. We are not saying that the next states are the same, they are equivalent, right. And what does equivalence means? It's by this definition that the outputs should match, right. So it's very easy to see that any finite state machine, you can replicate a state by just duplicating it out. So then that becomes an extra state. You can minimize it and get rid of that. So when you are comparing m and m dash, we make no assumption about whether m and m dash are minimized or not. So it is quite possible that they don't have the same number of states. So the necessary and sufficient condition for two states to be equivalent is that for all A, this is equal to this and this one is equal to this. So this is a result that has been proven. So we just defined it like this here, and then we show that that is in fact the necessary and sufficient condition, okay, and equivalent states can be merged. So here we were talking about two separate machines m and m dash. Here we are talking about only one machine, but we are looking at two states in that machine m, and we are saying that these two states are equivalent, and therefore we can minimize the machine by merging them. We are going to look at an algorithm which systematically does this thing. Let us now come to the definition of product of two automata. The product automaton of two automata m and m dash is defined as another automaton. That automaton has the states as q cross q dash. So we concatenate the state of m with the state of m dash to get the state of mp of the product machine. We have sigma is the input alphabet, so these two have the same input alphabet, okay. The output alphabet is only boolean, so 0 or 1. So the way we are defining this product is that if the outputs of the two match, then the output of the product is 1. If they don't match, then the output of the product is 0. And then we have the transition function, which is defined like this, that it is q cross q dash. So this is a global state. The global state, when presented with an input, goes to another global state, right. And under the constraint that if the global state was q q dash and you presented the product machine with A, then the next state will be, the next global state will be delta q A according to this delta, and delta dash q dash A according to this delta dash, right. So the individual machines make transit to their next state, and the concatenation of those next states gives you the global next state of the product machine. And the output function is defined like this, that lambda p, the output of the product, when it is in a global state q q dash and on input A, it becomes 1, the output is 1 if the output of the individual machines m and m dash match. If they are equal, then the output is 1. If they are not equal, then the output is 0. Okay. All right. So can we say something about the equivalence of the two machines from this? If we take the product, huh? All outputs should be 1, right? Isn't it? That's what we feel should be the definition of equivalence between these two state machines. Now, okay, so we are going to come back to to the computation of the equivalence between the two state machines, we will see that it's slightly more complicated than what it seems here. Okay, and we'll come back and explain why it is like that. Right now, let us come to the definition of acceptor. So far we have just talked about state machines. We haven't talked about goal states. We have not talked about states which are accepting states of the automata. Now, finite automata are also widely used for as acceptors. So, for example, that you want to write a state machine which is going to produce an 1 only when a particular input sequence comes. Right? So, that is called an acceptor for that. Right? So, if we want to do that, then what we will have is that in the finite state machine we will have certain states which are marked as accepting states, right? And whenever the automaton reaches those states, we will say we have accepted it. Now, this accepting state concept has been extended in various ways. So, the most primitive form is that in the state machine you have one or more accepting states, and if you reach any one of them, you say that the input sequence is accepted. And if you do not reach any of the accepting states, then you say that the input sequence does not belong to the language which is accepted by my finite state machine. Now, there are the variants of this is when you say that the accepting states must occur infinitely often, or you say that there is a state set, okay, and all states in that must be reached, or some state in that set must be reached, okay, in order for the sequence to be accepted. So, there are various definitions of this acceptance, and we will see that for equivalence checking we will need one kind of definition, and for property checking we will require another kind of definition. Okay. So, a deterministic finite acceptor called DFA is a 5-tuple q sigma delta q0 f, where q is the finite set of states, sigma is the input alphabet as before, q is the transition function, q0 is the start state, and f, which is a subset of q, is the set of final states or accepting states. A finite sequence is said to be accepted by the machine if delta star q0 with the input sequence A belongs to f. So, when you apply the input sequence A, the state that you reach at the end of it is it belongs to the accepting sequence. Okay. Now, this is something which we are talking about is finite sequences, right. So, we are talking about the last state in that is reached by that sequence, and that last state must be one of the accepting states. Now, what are we going to do about infinite sequences? When do we say that an infinite sequence is accepted? So, one of the accepting conditions of infinite sequences, which we shall require in our property verification later on, is called the Bucchi acceptance condition. So, in order to understand that, first let us see the definition of a Bucchi automaton. An accepting Bucchi automaton is a 5-tuple like this, where q is the set of finite states, sigma is the input alphabet, and q delta is the transition function, exactly as before. Q0 is the start state, and f, which is a subset of q, is a set of final accepting states. So, this definition has nothing different from the definition of the normal finite automaton that we had in the last slide. The difference is in the acceptance condition. In the previous case, our acceptance condition was that when presented with a finite input sequence A, the last state that is visited at the end of the sequence must belong to the accepting set of states. In the Bucchi automaton, the accepting condition is that an infinite sequence A is accepted by the Bucchi automaton if for all t for all t, there exists some t dash which comes after t, and delta star qt, so starting from t, okay, and presented with the input sequence from there on, from t onwards to t dash belongs to f. So this, what this formally tries to say is that an infinite sequence is accepted if the final set is visited infinitely often. So f is the set of accepting states. So the trace, that is the outputs that are produced or the states that are visited by virtue of the infinite input sequence A, that state sequence must contain states belonging to f infinitely often. What do we mean by infinitely often? Take any point of time, in the future again I must reach a state belonging to f. Take any other point of time, from there in the future I will be reaching a state belonging to f. That is what we mean by it occurs infinitely often, right. So there is no last state belonging to f that you visit. It is not the case that you visit some state of f and then in the future you are never going to visit a state, then it is not an accepting sequence as per Bookey acceptance condition, okay. And we will see later on that all linear temporal logic formulas can be translated into Bookey automata, right, and that is where this notion of visiting infinitely often will come into play. So we are going to come to that when we talk about property verification techniques. So now with this background, let us start looking at the problem of equivalence checking of circuits. So far we are just talking about state machines and their acceptance conditions and equivalence and products and things like that. We now look at the equivalence checking problem for sequential circuits. So here we have two sequential circuits. Okay. Again, our definition is that the two sequential circuits are defined to be functionally equivalent if they produce identical output sequences for all valid input sequences. Then so they are like black boxes. Whatever input I give this one, I give to the other one, and I expect that the output should match. So I can look at this as the following thing, that each sequential circuit consists of some combinational logic and some delay elements. Okay. So D1 is a set of delay elements which belong to the first circuit. This is a combinational logic for that circuit, and this is the other sequential circuit which has D2 as the set of delay elements, and these are the combinational logic. Okay. And the outputs of these two are compared, and if the output of this XOR gate is 1 at any point of time because they are receiving the same inputs. So if we can create a scenario where the output of this is 1, then we have found that these two are not equivalent, right. Now see that to check whether this is 1, there can be a various types of approaches. One approach is that this whole thing is also a sequential circuit. This whole thing is also a sequential circuit. It has some combination logic and some this thing. So that sequential circuit represents some state machine, and we are trying to figure out, can we reach some state where this output becomes 1, right. So it's in that state machine, it's a reachability problem. Okay, that is one way of looking at it.
Sir, when the output is 1, then it should be equivalent.
If the output is 1, Oh, this is x naught. So when the output is 0, then they are not equivalent. So we want to reach a state where the output is 0. Okay, can we reach a state where the output is 0? So that we can reduce this problem to reachability in a finite automata. We can reduce this problem to checking the equivalence of these two state machines. That is another approach. A third approach would be to use ATPG. Have you studied ATPG in the testing track? Right. So what I do is I want to see whether we can make this 0, right? So we introduce a stuck at 1 fault here and then try to see whether we can cover that fault. If you can find any test sequence which covers the stuck at 1 fault here, then that must definitely drive this to 0, right? So you can use an ATPG, right? So there are variety of things that you can do. Now the thing which is most popular is that well, where do we need this equivalence checking problem? Equivalence checking is typically done when your design goes through the synthesis flow, right? So you first enter your RTL, then from that you create the gate level design, then you refine the gate level design, optimize it. There are many steps of optimization, and you want to make sure that after your optimizations are done, the circuit remains functionally equivalent to the previous thing, right? In the sense that for the same input sequence it should still produce the same output sequence, right? So that is where equivalence checking tools are used. Now typically when the synthesis takes place, the set of delay elements don't get changed. You optimize the logic, but the number of flops or the set of flops, they remain the same. Now if we say that that is the case, that the delay elements are not changed, then what we can do is we can try to solve the problem by checking combinational equivalence between these two combinational circuits, because combinational equivalence checking is much easier than sequential equivalence checking, because in sequential equivalence checking you will have to traverse the state space of the design, and in combinational equivalence checking you just compare two Boolean functions, right? So if we could solve the problem by combinational equivalence checking between these two combinational logics, then that's the ideal scenario. But the problem there is that you need to know that which flop here corresponds to which flop here. You need to know the mapping between the delay elements. If that is known, then it's easy. If that is not known, then again you have two problems. One is that if you expect that there will be a mapping. So there are two scenarios. See, one is that you know for sure that there is a mapping, you don't know the mapping. Right? You know that there is a mapping, there is a correspondence between the registers, but you don't know the correspondence. Then you can find out the correspondence and then use combinational equivalence checking. And if it is the case that you don't know whether there is any correspondence between the registers, then your problem is the most difficult, most generic and most difficult problem. Okay. Then we are going to look at equivalence checking algorithms for sequential circuits, right? So this is the steps through which we shall go through. So let us look at the equivalence checking paradigms. The first one is sequential equivalence checking, where we compare state machines. The second one is combinational equivalence checking, where we compare combinational Boolean functions. And if one-to-one correspondence between the registers is given, then sequential equivalence checking can be solved using combinational equivalence checking. And this is a very popular approach, and there are a lot of tools that are available which do this. So, in combinational equivalence checking, we compare the output function and we compare the transition function. Right? So, we have to compare that this lambda 1 and lambda 2 are equivalent, and we have to compare that delta 1 and delta 2 are equivalent when we have a register correspondence. Right? So, that is what we are doing here. We are feeding them with the same inputs, and what we are doing here is, see, if you look at this slide, in the what is going, the output of the flops are going back into the combinational logic, right. Here also the output of this is going back into the combinational logic, and the input of the flop is coming from the combinational logic. So, when we have the register correspondence, what are we going to do? So, suppose there is an input here which comes from a particular flop, okay, which comes from this flop, okay, and we know that that flop corresponds to this flop here, okay. Now, what we will do is that we will tie up these two and then remove this and remove this, right. So, because we know that these two registers correspond to each other, so we tie up the output of the registers of the corresponding registers and then feed that into the places where the original registers were feeding into, okay. All right. So, with that transformation we get something like this. See, this is the register outputs, they are no longer coming from this, they are feeding into the combination logic, right. And then for all values inputs of this register, so let us call this S, because this represents the state, right. It used to represent the state, this used to represent the state. So, for all states, for all inputs, whether the same outputs and the same next state is being produced, the output should match, the next state function should match, right. So, that is what we try to do. Is this part clear? That what exactly is being compared and how we are converting the two sequential circuits into combinational equivalence checking? Clear?
So besides correctly, we are also getting the other input as.
We are cutting out, we are taking the outputs of the register. So, let me draw it here. So, this is my machine 1, which has, let me draw this with two flops, okay, and then okay. Now, so let me call this AB, and there are some primary out inputs that are coming into the circuit, and there are some primary, so I1 O1, this is I2 O2, and let me call this X and Y, and let me call this D1 D2 and R1 R2, right. Now, suppose we know that D1 corresponds to R2 and D2 corresponds to R1, we are given this correspondence, let us say, okay. So, what we are going to do is we are going to take out this combinational logic, okay, and take out this combinational logic, right. Now, we know that D1 corresponds to R2, right. So, this is D1 and corresponds to R2. So okay, and let me call this S1, and I will have S2 okay, and I will tie up the inputs. Remember that equivalence makes sense only if they have the same input and output alphabet. Now there are two things that we need to compare. One is the output functions, so O1, O2. Other thing that we need to compare are these, right? Yeah, the state out. This and the other one. Okay. So this is the equivalence checking that we want to do. Check the combinational equivalence of the transition functions, the next state functions, okay, which are these, and the output function, right? All this was possible because we were given this, right? So in the next lecture we will now see that how we systematically take this approach and compute the equivalence between two sequential circuits, and we will also look at how to compare state machines when the correspondence is not given but known to exist, and also when it is not known to exist also.